share my PPT now. Is my screen visible?
Yes, ma'am.
Okay. So unfortunately today I didn't launch the question and polls since I was not so sure whether the students will join or not. So you can give all the answers in the chat box itself. Okay. Okay. I hope you guys got it. Let me share my screen here. Like, sorry. So last week we saw about, okay. Good evening all. I'm Nilakanmani. I'm one of the TAs for the NPTEL course Characterization of Construction Materials, and today we're having the live session for week 11 content, that is porosity and pore structure, mainly using mercury intrusion porosimetry. Okay, so let me start sharing the questions for week 11 content. So last week we saw about spectroscopy, and this week there is some small content from spectroscopy, but majorly I took the questions only from MIP. Okay, so here is the first question for this week. The question is, the threshold pore size is indicated by which of the following options? Okay, let me start a timer for a minute. There are 4 options available. You have to pick the right option from here. Please give your answer in chat box. Time is up. Let's see the response from here. Okay, option B. Let's see what's the right answer. So if you see, uh, all of a sudden there will be a sharp increase in the intruded volume. From this graph, we'll be able to understand that. We can see there is a sharp increase in the intruded volume. So that is known as the threshold pore size. So the correct answer is option B. So now let's move to question number 2. Question number 2 is the, yeah,
Actually, there's a doubt, ma'am. Actually,
yeah,
whatever we cast the cubes, the size of the
yeah.
cube is almost 150 by 150, ma'am. Generally, in
Okay,
general,
okay.
the sample size is very, very small as compared to the specimen.
Yes,
If we find the pore size or the pore structure of in that particular sample, what we have taken out of that huge big cube,
yeah.
is it relevant that the same pattern will be available in the entire cube as such? Because
Uh,
when we compare, the cube is only 150 by 150, but when we really come onto the ground and cast the real thing, it will be in terms of meters and something like that. A huge building, for example, ma'am, or a huge big structure. And here we are doing a sample examination in all these, whatever sir has taught the methods, we are taking a small sample.
yeah,
Phase is okay, ma'am, where we study the phase difference and the changes in the phases. That's okay. There we can understand, yes, this would be the pattern in the entire structure as such. But how about the pore size, ma'am? Because the pore size in that particular sample may be different at any other place also.
okay. Okay, let me give your answer. See, when it comes to characterization, I think if you remember the intro to CCM class, sir, as Manus has clearly explained, the structure is actually in the macro scale. And when it comes to laboratory experiments like compressive strength, we do it in centimeters kind of range. But when it comes to characterization, we take very, very less. And if you think about FTAR, only 1 milligram of sample is required actually when testing. And when it comes to XRD, we take about 100 milligrams of sample. So in all the cases, when you take a sampling plays a very important role when you do characterization of construction materials. You have to know how to pick the correct sample. See, initially we'll make some mistakes in doing this. So initially we need to repeat and get to know how we have to take this sample, and we should know uh, if you take a pore size from the edge of the cube, if consider this to be a cube, if you take sample from here, the pore size distribution can be different from here. So it's always better you have to take the chunk from the middle portion of the cube. And also when you break the samples to take the chunk, while breaking, that mechanical impact is there, that can actually introduce some micro cracks into the sample, so that also can play a significant role. So whenever it comes to characterization using sophisticated techniques, we have to be very, very careful uh, in the sampling time, how we sample the material for testing. So when it comes to MIP also, if you have some doubt, but it should be same if you take the samples from the core, and if you're taking consider you're taking four different samples. Uh, Say you take OPC cement and you take slag cement and you take fly ash cement cubes, cement mortar cubes. Then you can compare how it is different from OPC to uh, slag to fly ash, and whatever results you get from here is the representation what you interpret from the technique you use. It may not be the true representation, but you are interpreting something out of the technique you do. Okay, they as you if you read the advantages and disadvantages of the particular technique, there you in particular to MIP, they can be ink bottle effect can be there, which can show predominant increase in the smaller pore size fraction if there is ink bottle effect. Which I have a question for that particular thing, so we can discuss about that in the later slides. I
So,
hope
ma'am,
you
what do
got
you
it.
generally suggest, ma'am? In one cube, say for example, 150 by 150,
Yeah.
how many samples we need to take out and study, ma'am?
See, since
Because
this, yeah,
these all methods are very very costly. I had when gone for SEMM for one sample, they took 5,000 from me.
yeah, it happens to everyone.
So, what is the parameter? Like you only are trying to bring out that the edge might not have might have already hydrated and the cement particles and the pore structure may have developed very well, but the internal when we come to the core of the concrete of the cube, the hydration might have not completed, and the pore size or the pore structure may be different there also.
No, 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 no. You're talking in a different way. I think you have to understand this point. See, when it comes to the edges, wall effect can be there. When you compact the concrete cube, due to wall effect, uh, compaction might not be proper, and they can be more as you said, see, even if there is curing, if it's underwater curing, it's fine. But if it's a normal curing thing, uh, a normal curing of its air cured, the outer area might not be properly cured. But if you take the core area, drying is not possible from here. See, concrete has to dry it first. It will dry it from here only, not from the inner portion. And normally we say since the outer portion is subjected to chemical attacks, any other chemical intrusion and all, so the outer part controls the durability, and mostly the inner portion will not be subjected to drying or any other parameters or uh, disadvantages that we face from the outer side of the cube. Okay.
Understood, ma'am. That was taught in concrete
Ah,
technology that
okay.
the outer phase gets exposed to the environment, so the water
So,
is over,
mm, so it's
whereas
better.
water will be present inside.
Yeah, so it's always better to take the sample from the center. And if say if you're taking sulfate attack samples, so sulfate attack will happen mostly in the outer side. So in that case, you have to take samples. See, and some consider this to be a sulfate attack sample. So mostly we'll take samples from here, and we'll do MIP here. So here the pore structure will be different. And if you take an unaffected area, okay, so this portion, not much gypsum will be formed, and the pore structure will be more intact here than here. Here it might not be intact. Understand, no? So we should understand why we are doing the characterization. So in that way you'll get to know where we have to take the sample from. If we have to compare two different cement systems and only the effect of curing or how does the reaction kinetics has affected, you have to take the samples from the center of the cube. And if you need to take, and if you want to understand the uh, chemical phenomenon or attack or carbonation kind of thing, then you have to take zones which are affected, which might not be affected, and you can compare.
Okay, ma'am.
Okay. And when it comes to repetition, mostly we don't repeat. If you ask me, I don't repeat. But initially, I do one or two trials and understand how it's actually going, and then we decide. Better you join. I hope there is one more live session with the professors. I guess if that is there, please join and place these queries if you're really interested to know about this more. Because I am a student, so my perspective will be different. So if you want to know better, you can join that live session and ask the question.
Yes, ma'am. I'll do that, ma'am.
Yeah, okay, thank you. Now let's move to the next question. So here comes question two. It's a true or false question, so I'll put the timer to 30 seconds. The statement is pore volume is a very good indicator of the material. Pore volume is a very good representation of the material characteristics rather than pore size. Is it true or false? Please give your answer. Please give your answer in chat box. Time is up. Option B. I think I don't find any other response apart from KPC Rao. There are Naina and Javed in class also. Please try to answer. Okay, fine. Okay, now let's. So here the statement is given in the, this particular snap is from the lecture PPT. So in the slide study of porosity, it's given pore volume is not a very good indicator of the material. Rather, pore size distribution is significant, which means if the statement is false, so the correct answer is false. So here I have to tell one thing. So when it comes to pore volume, it doesn't show which pore size is particularly higher or lower. But when it comes to pore size distribution, it tells you which particular pore size is uh, higher or lower, or what amount of percentage of particular pores is present. That we can get to know from pore size distribution. So it's better to understand the pore size distribution rather than pore volume. Pore volume, if you take, if a particular sample has very small pores, but the total volume will be 10 centimeter cube. But if you take a one particular cube as only one pore, that can be equal to the size of 10 centimeter cube. So in with that regard, we should know the pore size distribution rather than pore volume. I hope you got it now. Now let's move to question number 3. Now I have given you two graphs here. Okay, graph A and graph B. You have to compare both graph A and graph B and try to understand what is different here from the pore size. Okay, I'm talking you to understand about the pore size. So you have to consider only the differential graph here. Okay, so and try to understand what is different in both these things. Okay, so let me start timer for a minute. You have only two options. And try to understand which particular thing has okay, here there are three numbers. No, let's consider the black one here. Okay,
Coarser means what? You want to say the pore size has reduced Smaller
Coarser
or
means it's bigger. Coarser means it's bigger.
bigger? Okay.
Yeah, bigger. Okay. Let's assume the black one as the only thing to compare. Leave the red one and the blue one. Take only the black one and then compare. Yeah, coarser means bigger pore size range. Time is up. Okay, option B. Let's see. I think the correct answers are mostly option B. Okay, I think it doesn't repeat hereafter, I guess. The correct answer is nothing but option B. Yeah.
Actually, this you should have mentioned about the water bender ratio for B also. Then only we can say that based on the water bender ratio only these graphs can be read, man. As the
Actually,
water bender ratio reduces, the pore size reduces.
actually, these both are not the same graph. This one is from a lime plaster mortar. Okay, and this is cement system. So these both are different. So, sir, I've mentioned lime plasters, which they use it for historic mortars with which the historic buildings have been constructed. The pore size are coarser in lime plaster because that have more breathing capability, but in when you compare cement system, it doesn't have that breathability because the pore size are very finer, and that kind of breathability will not be expected from cement system. Okay, let me take the pointer. So from cement system we can't expect such kind of behavior. So see, we need when it comes to historic structures, mostly it's masonry structures or stone masonry, brick masonry or stone masonry. So there will be a unit, and above and below the unit there will be a brick mortar to bind it together. So usually they consider the binder to be a weaker unit and brick to be a brick should not fail. The mortar can fail. Okay, so they work in that perspective. When it comes to structural design, we say that weak beam and strong column, right? So it doesn't mean that the beam should fail, but the beam can fail, but the column should never fail. In that way we design the building, because if the column breaks, the whole unit will break. In that similarly, in when it comes to masonry structures, they consider brick should not fail, but the mortar can fail if it's subjected to a marine environment or strong or chemical exposure. It can happen in that way. So they can take the brick unit and they and put a repair mortar, and they can put the same brick, or if the brick is also damaged, they can put a new brick and do the repair work. So in that case, normally for that thing, uh, the the historic structures have a lime plaster which has more coarser pores than compared to cement system. And normally that's why if we use cement mortar to historic structures, normally the structure soon the repair fails because it is not compatible to the system, uh, how it's actually constructed. Okay. Now let's move to question number 4. Now, sorry, I think the wordings I've done, I didn't correct. So you have to match the type of pores to the pore diameter. Okay. This is a question. Let me give a timer for a minute. Please match the pore type of pore with the pore diameter. Time is up. Okay. BC. That's right answer. The name itself suggests macro means it's big, meso means it's middle, micro means it's very small. It's a very, very simple question. So here is the right answer. Macropore means its pore size is greater than 50 nanometer. Meso means it lies in the zone 2 to 50 nanometer, and micro means it's smaller than 2 nanometer. Okay, so B, C, A is the right order. Okay, so now let's move to question number 5. And this one is also available in the lecture PPT. Within first few slides of the PPT, we can see this thing. Yeah. So moving to question number 5. Which among the following suggests a higher degree of distortion or disintegration of microstructure of a material from an MIP test? Okay, so you're doing an MIP test, and from that you get a pore size range. Okay, so in that, uh, we are taking that the sample we took has a higher degree of disintegration of the microstructure, which means we can assume uh, uh, take a sample which we take for compressive strength measurement. So obviously there can be lot of micro cracks within the sample, no? So or else consider a sample which is subjected to marine exposure or any other chemical environment which will affect the microstructure or which will disintegrate the microstructure of the material. So in the sample is subjected to disintegration. So in that case, what you can expect from the MIP test? From the following options which can be observed. Okay, it has more than one option, so please go through all the options. I'm starting the timer for a minute. Time is up. Okay, no answers seen. Fine, let's discuss the problem then. So the right answers are okay. Before that, we'll read the options. A right shift in the critical pore size to coarser sizes, which means when consider to be normal OPC cement concrete itself, the concrete cube you're taking for compression test. When it's subjected to compression, obviously there will be lot of micro cracks once it loading reaches 30% of the ultimate load, right? So in that case, there will be lot of micro cracks once the compression test is done. So in that case, obviously the pore size can move to a coarser size, or consider a sample that is taken from any other aggressive chemical environment. So in that case also, so the available portlandite will be converted to gypsum, and the gypsum will erode, like it may dissolve and reach, if it's a freshwater surface like a river structure. So obviously that will erode along with the moving water. It may dissolve and move with the freshwater itself. So in that case, it can dissolve and it will leave the uh, it will leave the concrete itself. Okay, so if I think the way I explain is a bit complex. So if there is a fresh water going here and if there is a concrete, obviously some of the elements which is susceptible to easy chemical attack, it will obviously go off, right? So in that case, the pore size will shifted to a coarser size. So the correct answer can be option A. Yeah, it will be option A. And there is a sharp decrease in the threshold pore diameter. That is not possible because then seems to be a finer size range. So that is not right. And option C is widening and increase in the number of peaks in the differential intrusion curve. So if you take a differential intrusion curve, normally it will be like this. Okay. So what happens? A particular size range, a particular phase is there. A particular phase is eroded. Then there can be increase in a particular size range, particular pore size range, because whatever phases is present uh, is removed, right? Okay, I'm talking in a wrong sense. Okay, assume a concrete is here, concrete sample is here. There are some pores here already, right? And all of a sudden, uh, Portlandite wherever is there, it gets eroded off. Okay, so obviously there is increase in the pore size wherever Portlandite is there. So if this is the normal, wait, erase. So, so normal pore size range is 1 point. Let's assume this is 1 micrometer. Okay, normal pore size range. There is increase in the pore size range because the Portlandite goes up. So in that case, normally it will not happen in the way I explain, but for the sake of explaining, I'm trying to explain in a simpler way. So this particular size range is in the range of 10 micrometer. So what happens? There will be increase in the 10 micrometer zone also now. So there will be multiple peaks compared to a single peak. There can be multiple peaks because of introducing new coarser size ranges. Okay, and a dip in the differential curve volume curve, it can't be expected because of distortion or disintegration. Okay, so now let's move to next question. Question 6. Which of these factors affect both porosity and permeability of concrete? It's a very, very simple question. If you understand cement chemistry better and if you have gone through all these lectures, we would have talked about these topics in between somewhere. Okay, let me start the timer for a minute. Please go through all the options. It has more than one right answer, so please be sure while giving your answers. Here we have explained few parameters in the lecture PPT itself, how certain things can affect porosity or permeability. Time's up. No answers here. What happened? Are you guys still in the class? Okay, it's a quite simple question. So the correct answers are option A, B, and D, E, because water to cement ratios professors have already discussed in the class itself how water to cement ratio can affect. And when it comes to degree of curing itself, they have compared 7-day, 14-day, 28-day kind of porosity graphs. So, and type of cement, obviously, if you have OPC and if you have fly ash or slag to it, or LC3 type of cement, it will affect the pore structure porosity. And in these things, yeah, use of mineral admixtures also makes the same sense. Like when you have some mineral admixtures like fly ash or slag or LC3 type of mineral, LC2 type of mineral admixtures, it can affect. And use of granite aggregate might not vary the porosity. Okay, that is not the right option. So the answer is A, B, and D, E. Okay. So now let's move to question number 7. Which of the following aggregate is having a finer pore structure and why? So here we have two types of aggregates. One is cold bonded aggregate, and let me start the timer for a minute. So here we have two types of aggregate. One is cold bonded and one is sintered. And they're giving you two type of reactions for that. So either due to chemical reaction or high compaction, which can have a fine pore structure. Okay. Please give your answers in the chat box. Please respond. We just have one or two more questions, and that's it. We can leave. Time is up. This question is directly from the lecture PPT only. Okay. Oh, maybe my system is not updated until then. Okay, thank you. I didn't see the response properly. Okay. So you have given option A. Let's see what's the right answer. So this particular snap is from the lecture PPT. So here they have compared both cold bonded aggregates and sintered aggregates. And we could see the cold bond aggregates as a finer pore size range. So the answer is correct answer would be cold bonded aggregate. And either it can be due to chemical reaction or high compaction. Cold bonded aggregate means it's not sintered means it's put at higher temperature. And cold bonded aggregate means it's mixed with cement and water. Cementitious material will be mixed with water so that it will react and form finer pore size range mainly due to chemical reaction. Okay, not due to high compaction. So the correct answer is cold bonded aggregate and chemical reaction. Cold bonded aggregates are formed at normal temperature from normal room temperature to maybe we can put them at higher temperature for a higher degree of reaction. Like around 60 or 70 degrees Celsius, maybe we can increase the kinetics of the reaction. So we can, but when it comes to sintered aggregates, we put them at very high temperatures like 1000 degrees Celsius or above 900 degrees Celsius for sintering reaction to happen. Okay, both are different. And when you compare both, cold bond aggregate will have a finer pore size range. So this is a problematic question. I don't know whether uh, you guys, is this question discussed already in previous classes, previous live sessions? Okay, if at least one person have not attended, saw this question, that'll be fine. So the question 8 is, so here they are given two pore sizes. This black color shaded area is the pore. Okay, they are given the pore height as well as the pore width. Here the pore height in sample A, I'm telling you, the pore height is 6 centimeter and the pore width is 4 centimeter, followed by, so this is assumed to be a concrete cube and this is the pores. Okay, so here followed by that there is a smaller pore. One is 2 centimeter width and 2 centimeter height, and next there is a long pore which is the width is 6 and height is 1. Okay, so sorry, length is 6 and height is 1. And similarly in sample B it's quite different. Okay, you can see the difference here. There is a larger pore size followed by smaller one, and here there is a larger pore size followed by smaller one, and all of a sudden there is a very big size of uh, very bigger size is also there. Okay, so in MIP we know that uh, when they when this when there is increase in the pressure at lower pressures, larger pore sizes will be filled, and when it comes to higher pressure range, finer pores will be filled with mercury. That is the assumption. So that's why we keep the sample size to be very small so that the mercury will intrude from all the directions. Okay, so in that case there is one more question. Ninth question is there, that there we can discuss about what is different from sample A and sample B. So now we have to calculate what is the total interconnected porosity in sample A and sample B. So in all these cases, there are interconnected pores. So you have to multiply and find the area of the total interconnected porosity. Okay, let me start the timer for a minute. Please find the total interconnected porosity of A and B. If assuming that only till this 2 by 2 is there, then we will say 6 into 4 it will be 24, and then if you multiply 2 by 2 it will be 4. So 24 plus 4 it will be 28. So then next you have to multiply this and add this. So totally you'll get the interconnected porosity. Okay, time is up. Let's see the class response. Okay, there is no response here. Okay, then we'll see how to calculate it. So in this thing, where is draw option? First, I'll take this and I'll calculate here. Okay, so when it comes to so here in the first sample A, it will be 6 multiplied by 4 plus 2 multiplied by 2 plus 1 multiplied by 6. So that will be the porosity. So 6 fours are 24 plus 4, 2 to the 4 plus 6. So totally it will be how much? 34. So similarly, can you calculate for sample B and tell me what is the total interconnected porosity? Yeah. Okay, I'm sharing the screen. Please calculate. Are you guys able to understand? Okay. I think since there is no response, we'll start. So similarly, if you multiply 6 by 2, it will be 12. 12 plus 4, 16. 16 plus 2 is 18. 18 plus 4 4 is 16. It will be 34 again. So the answer is 34 for both the cases. And what type of effect you can see? Uh, ink bottle effect will be observed in which sample? Either in sample A or sample B, or in both samples we can observe, or none of the samples. So what is ink bottle effect? That you should know. Okay, since there is no response, let me immediately share the answer. So we can observe ink bottle effect. So when it comes to ink bottle effect, what does this say is, uh, so here we assume the pressure, you take 4 dia here and we'll take pressure here. Okay. Yeah, I think I'm drawing the diagram wrongly. I'll put dia as like this. Okay, so I don't know how to write. Okay, yeah, it should be like this. So when the pressure is high, yeah, now I think I'm drawing it right. So when the pressure is very low, then the very low, it will fill the very smaller pore size ranges. And when there is increase in the pressure, it fills the very fine pore size range. So when it comes to mercury intrusion in the sample A, so initially there is a bigger pore, which means the at low pressure itself will get this will get intruded. So we'll assume it will be a bigger pore only. Then when there is increase in the pressure, then it will enter uh, second it will enter the second pore 2 by 2. So there will be increase in the pressure. In that case, it's a very smaller size. And further, there is increase in the pressure. It is a very small pore and a wide pore also. So it needs increase in the pressure to let the mercury intrude into this pore size. So in that case, we can understand from this graph. So here what happens? So when there is a certain amount of pressure, this bigger size will, bigger pore will be intruded, and there is further increase in the pressure. This 2 by 2 pore and 1 by 2 pore will be included. And what happens to this 4 by 4? This doesn't have any other contact to for this to assess this pore. Okay, so what happens when there is further increase in the pressure? This pore gets filled. But what it will actual pore size is this, but when it comes, how we interpret it is how we interpret actual, it seems to be like this, but how we actually see is there will be a bigger pore followed by a 2 by 2 pore and followed by a very narrow pore. Sorry, very narrow and like very wide small pore. Okay, a longer, we will say it as longer, uh, a longer smaller pore. Okay, I think I'm confusing, but when it comes to sample A, there will be a bigger pore followed by a smaller pore. So this will be interpreted as such as. But when it comes to ink bottle effect, because of ink bottle effect, this happens. But actually, this is not the case. This is the true. So we'll not be able to interpret this type of structures using MIP because of ink bottle effect. This is one of the disadvantage of this technique. And this is the last question. I hope you guys understood question 9. We can leave the session then. Is there any other query? Is there any other query? If there, you can type in the chat box. Okay. Okay then. Then we can leave the live session. Thank you so much. And sorry for the inconvenience happened in today's class. Let's try to avoid this in the in the forthcoming classes. Thank you all.